Hello Internet, Oscar released again with another video, this time showing you how to find the interval of convergence, as well as how to widen that interval. When it comes to finding roots, only bisection and false position method actually have a guarantee of convergence. That's because the interval that they use, a and b, force the function to cross the x-axis somewhere in between. Newton-type methods don't have this same guarantee of convergence unless you find the interval of convergence. Newton-type methods are root-finding approaches with this form, that have a Newton step and a Newton update. So Newton's method is a Newton-type method, but so are secant method and finite difference method. All of these you are interested in finding the interval of convergence for. Let's look at an example of a function both converging and diverging when we try to find the root. This function we'll use the arctangent, and the approach we'll use to find the root is Newton's method, which means we also need the derivative. In this case, it's 1 over x squared plus 1. We'll start from 3 points, the value of 0.5, the value of 1, and the value of 1.5. Here's what the arctangent looks like, and the root is clearly 0, but that's not really what we're looking for. We want to find the interval of convergence. So if we use Newton's method, starting at the point 0.5, it takes about 3 iterations to start converging on the root. And if you start at the value 1, it also clearly starts to converge. But if we start at the value 1.5, this causes our root finding method to start to diverge. Here I plotted out all of the points that we used in our tests, and we'll show green squares for when they converged and red x's for when they diverged. I also plotted out the negative starting points to see if they also converged or diverged, and it's pretty clear that anywhere between -1 and 1 will converge, and any point outside of -1.5 and 1.5 diverges. But when does it go from converging to diverging? That's what we want to find. We want to find the interval of convergence. So how do we find that interval? Given some function and an error threshold, we'll use a few test points to see when they start to converge and diverge. We'll then take a new test point midway between those two important points and replace it depending on the behavior of the function. This is essentially bisection. Using our example from earlier, we know that everything up to 1 converged and everything after 1.5 diverged. So we'll take the midpoint and test it using Newton's method a few times. And it looks like this one is converging, so we'll add this to our interval of convergence. Now we repeat the process using a new value for c and d. Take the midpoint and start using Newton's method. And it looks like this one's also converging, so we'll add it to our interval of convergence. Again, we take the midpoint between c and d and test it using Newton's method, although this time it looks like it is diverging. So we'll exclude it from our interval of convergence. And we keep repeating this process until c and d come together. Here are our actual numbers for c and d as we iterate through them. But this is only one half of the story. What we need are both sides of the interval. So if we look at this, our actual interval of convergence is between -1.39 and 1.39. This is that same interval graphically, but what we would like is for a way to expand that interval. Recall this form for a Newton-type method. We'll do one small change by adding a variable gamma. This is a damping factor. It's a number between 0 and 1, not including 0. When gamma is 1, it's like normal. We take the full Newton step. But when gamma is less than that, you take only a partial Newton step. Let's look at an example where gamma is equal to 0.9, and we start at the divergent point of 1.5. With the gamma of 0.9, the point that usually led to divergence, 1.5, now leads to convergence. This is because we don't take the entire Newton step. So we don't use a normal value for x2, we only take a part of it. Now our interval of convergence is actually between -1.57 and +1.57, but this is actually with a very large value for gamma. With a very small gamma, we can actually start much further away, in this case the starting point of 4, and still lead to convergence. With our value for gamma being 0.1, our interval of convergence is actually now between -13 and +13. Some things to keep in mind. The interval of convergence depends a lot on the function you're using, the value for gamma, and the root finding method. There can also be outlier points outside of your interval that lead to convergence, normally if your function isn't behaved well. And there also can be multiple intervals of convergence, usually if you have multiple roots and they're spaced far away from each other. Also, these intervals usually don't have to be symmetric. In our case, they were for the arctangent. In practice, you usually start with a small value for gamma and then increase it as you iterate through your function. And even if you're not interested in finding the interval that converges, you can still use gamma to avoid divergence. The example code that I use to generate these graphs will be hosted on GitHub. Thank you for watching. If you have any questions, comments, concerns, or other suggestions for videos, please be sure to leave them in the comments.